First of all, to show that question, how are we going to show that? Well, we can plug in 0 for x and 7 for y, because we know that point is on there. That's on our original function. Once we plug all of that in, anything to the power 0 is 1, and so that shows us that our a value has to be 5. Now we're told that f of 10 is approximately 2.67. We're going to find the value of k. So now we can plug in 10. We already know that a is 5. And solve along the way. Once you get the exponential by itself, remember solving for a variable in an exponent, you're going to have to take the log of both sides. Here it makes sense to take the natural log of both sides. I guess technically, since we were using rounded value of 2.67 all the way through, we would be fine with approximations, although you will not be dinged on your exam because they will not have, most likely, maybe as the final answer, they may have a mark assigned for the approximation sign, but usually they don't have a mark assigned for the approximation sign. The more often you're going to lose marks on the approximation sign stuff in your IA, in your mathematical presentation part for part B. So now that we've found k, we can find the derivative. So we plug in the a value of 5, the k value of negative 0.201. We take our derivative. It has a chain rule. Remember, the derivative of e stays the same, but then in the exponent we have another function. So the derivative of that is negative 0.201. And multiplying that by 5, we get a simplified function. Now, something about e to the x. What does the graph of e to the x look like? So we remember that e to the x looks like this. And if e to the x looks like that, then this graph here is going to be a vertical flip over the x-axis and stretched a tiny bit, because we got 1.005. And then inside the negative 0.201 is going to be a flip over the y-axis. And since that's less than 1, it's going to be stretched as well by about 5, because that's close to 1/5. So if we imagine this normal graph of e to the x getting flipped down, stretched a little, then flipped over, stretched a little, can you see what that's going to look like? Something like that. Can you see that your asymptote is not going to move? Your asymptote that was at y equals 0, what's the only way from our transformations that that asymptote moves? Is if you shift something up or down. But stretches and compressions aren't going to affect that. The key thing that I want you to notice from this is that f prime here never equals 0. So if we were finding our critical points to find out where our function was increasing and decreasing, when we draw our line, there would be none to put on there. And so now we could pick any point whatsoever to plug in to find if our function is increasing or decreasing. So if I plug in 0, because that's an easy one, e to the 0 is 1. 1 times negative 1.05 will be negative. And this function is always decreasing. So looking at this, This value is negative e to the negative 2.01. Just looking at this section, that section would always be positive. And so our first derivative is always negative, which means that our function is always decreasing. And what's the horizontal asymptote? Again, to find our horizontal asymptote, we look at our original equation. We imagine what's the limit as x goes to a very, very big number. And as x gets larger and larger and larger, can you see that this, here's our original function. I could write our original function with a positive exponent if I wanted to. And if we look at that function on the bottom, as x gets bigger and bigger and bigger, can you see that the bottom of this fraction is going to get larger and larger and a bigger and bigger value? And if you have 5 and divide it by a very, very large value, you're going to get very, very close to 0. But then we add 2 to a number very, very close to 0. And 2 plus almost nothing is still going to be close to 2. So that's how we can write down the equation of our horizontal asymptote.